Let's begin with something fundamental. What exactly happens when current flows through a conductor? Imagine a wire with 2 points, A and B. If there's a potential difference between them, charges move from higher to lower potential. That potential difference, let's call it V, is equal to V of A minus V of B. Now, say a charge, let's call it delta Q, flows through the wire in a small time interval, delta T. Then the energy lost by the charge is given by delta U equals negative I times V times delta T. That's because energy is leaving the system. In an ideal, frictionless world, this energy would turn entirely into kinetic energy. So you'd say delta K equals I times V times delta T. But reality isn't so generous. Charges constantly bump into atoms in the wire, and that energy becomes heat. That's why wires warm up when current flows. Now let's talk about where that lost energy goes, into heat. This is the magic of Joule heating. As electrons move under the influence of an electric field, they gain energy. But because they keep colliding with atoms, they lose it rapidly, and that lost energy heats the wire. The total energy converted to heat in time delta T is given by the formula delta W equals I times V times delta T. This is known as Joule heating, and it's why devices like electric irons and toasters get hot when switched on. The energy doesn't disappear. It simply takes a new form, thermal. Next, let's define electrical power, the rate at which energy is consumed or converted. The basic formula is power equals delta W divided by delta T, which simplifies to I times V. Now, if you apply Ohm's law, V equals I times R, you can derive two other important forms of power, P equals I squared times R and P equals V squared divided by R. These are known as ohmic power loss equations. You'll find them printed on devices everywhere, like 1000 watts on your heater. That's the rate at which it converts electric energy into heat.
But where does this power even come from? It's the battery or generator in your circuit that provides the electrical energy. In a battery, chemical energy is converted into electrical form. That energy then pushes charges through the circuit. The energy supplied by the battery equals the energy consumed by the components. That's how your fan spins, your bulb glows, and your charger charges, all thanks to electrical energy being constantly supplied and used.
Here's an interesting twist. In power grids, we often lose energy during transmission, and that can be expensive. Let's say the wires have resistance R sub C. The power lost as heat is P sub C equals I squared times R sub C. But from P equals V times I, we can write current I as P divided by V. Now substitute it in, and we get P sub C equals P squared times R sub C divided by V squared. This tells us something powerful, literally. Power loss is inversely proportional to the square of voltage. That's why power is transmitted at very high voltages to keep current low and thus reduce energy loss. And yes, that's also why those giant pylons carry lines labeled danger 11,000 volts. Let's solve a quick example. Suppose you have a resistor of 10 ohms and a current of 5 amperes flows through it for 2 minutes. First, calculate the power. P equals I squared times R, that's 5 squared, which is 25, times 10, giving us 250 watts. Now, calculate energy. W equals P times time, which is 250 times 120 seconds. That gives us 30,000 joules. That's 30,000 joules of heat produced in just 2 minutes. Enough to heat up your toaster or run an electric kettle. Alright, let's quickly revise what we've covered. When electric charges flow across a potential difference, they lose energy. Work done is delta W equals I times V times delta T. Power is the rate at which that work is done, P equals I times V. We've also seen the alternate forms P equals I squared times R and P equals V squared divided by R. And don't forget, power loss during transmission is given by P sub C equals P squared times R sub C divided by V squared. That's why engineers use high voltage lines. It keeps the losses low and the delivery efficient. I hope you now see how electric energy flows, gets converted, and powers everything from your phone to a power grid. See you in the next session where we dive even deeper into the world of current electricity.